Sitting down? Good. Hello everyone. Welcome to this event, live in the Bradfield Centre, live on the internet, brought to you by Digital Catapult and the Digital Security by Design programme. How can future hardware make our software more secure? My name's Matt Evans. Welcome. So since we're here in person and we've got the sort of the high frame rate, high def version, there's a few bits of housekeeping that we won't normally need to go through if this is just a streaming event. Fire can affect us. So there are fire exits. If there's an alarm, it's not a drill. Fire wardens will appear, do as they say, please. If you have a phone, please put it on silent. Please try not to mess with it while people are giving their presentations. If you need the loo, out there on the left. And so questions, we've got a Q&A session scheduled after 3 talks. So if you can remember your question until then, that would be perfect. Alternatively, those online, please tweet. There should be a set of tags appearing on the screen at some point. There'll be some tags that someone will read out at some point to tag your questions with, please, and where we can find them and funnel them into reality here in the room. So before I hand on to our first speaker, I was reading a nice article about there was an anniversary of the PDP-11 recently. I was thinking about the PDP-11 and the VAX and digital DEC, how they, in my opinion, I think changed the world with these 2 computers. And I would say that all of the machines that we use today, the computers that we have in our pockets, have got a lot to owe to these machines. So we have virtual memory, we've got multitasking operating systems, paging, medium-grained memory protection, well, memory protection compared to the machines that were there before, and you know, the sort of relatively modern environment. Windows NT is based on VMS, Unix, BIOS, the rest. So I've got a question in my mind that I was thinking of that came with this. What has changed since mid-70s? Let's be generous, to the early 80s. So imagine a computer of the early 80s. Only some of you are old enough to have used one, I think, but I'm definitely one of those. I'd like you to put your hands up, tell me what has changed in computing since the early 80s? Fundamental advances. Networking. Networking. Okay, cool. Yes, and the ARPANET was a thing there, but it's democratized. Yep. Oh yeah, security's become more of a problem. Okay. Yeah. Computers used to give you a clue. Computers used to be massive. They're now tiny. So they've gotten smaller.
Much higher parallelism.
Right, great. So much higher parallelism, lots more CPUs. But there's still each CPU, I would argue, is sort of doing the same sort of thing. Memory, I'll give you another clue. Okay, so there's memory, you know, thousands of times, tens of thousands of times more memory than was common even in the largest machines. And price, of course, they're cheaper. But I would put it to you that actually, fundamentally, what the processor is doing in the VAX and what the processor is doing in a phone of this sort of generation is very, very similar. You've got instructions that fetch things from memory, do stuff to that, put it back in memory. You've got an MMU that checks to a page table to, say, a 4K granule, and that's sort of it. We've still got malloc from Unix. We've still got free from Unix, right? We're still using the same sort of paradigms and writing programs that look very, very similar to the sorts of programs that were being written in the late 70s, early 80s. And for me, I think the reason for that is that we're now a victim of our success. Computers are too popular. There's so much money in computers. They're so useful that actually money doesn't like risk. And changing the way that we do something is risky. So it's quite difficult for our machines to change. So how do we do that? We've got some people here today that have, I think, done something that's quite a fundamental change in the industry. And they're going to tell us how they managed to achieve this. So up first, we have Professor Simon Moore from the University of Cambridge. Please welcome to the stage.
Well, thank you, Matt, and thanks for coming. It's great to see so many people. So yes, I'm Simon Moore. I'm one of many. There have been a lot of people working on this. I'm going to tell you a little bit about a project, sort of code-named CHERI. And really, it comes from the sort of thought experiment. We actually received some funding back in 2010 from DARPA. DARPA like to credit themselves. You know, they funded all the work on ARPANET, which became the internet. And I think one of the things they see is they've created this wonderful thing, but they've also created a problem that, you know, we get all of these attacks that come in over these networks. And so they feel some sort of responsibility, if you like, to try and fix this. And we were part of a program looking basically if you had a completely clean slate. So this is a great thing we can do in academia. Imagine there is no problems with backwards compatibility or any of that rubbish. I know, we all look. But it is an interesting thing to do in academia, is let's not worry about it to begin with. Why do we do that thought experiment? Is there somewhere we could be that actually would fundamentally improve security, robustness of our computer systems? And then when we figure out what it is, can we figure out a path between basically a PDP-11 and this new world order? Okay, so that's the sort of challenge. And thank you to Matt for his introduction, because when you think about it, a language like C, and we still write a huge amount of code in C, and even if it's a managed language or a functional language, often the runtime system's written in C, and the OS is written in C. You know, C was first run on a PDP-11, and I would argue, actually, as a machine target, really nothing has changed since the 1970s until now, and we have CHERI. And acknowledgement to sponsors. So, what is CHERI? Well, the unhelpful answer is we were in a hurry to think up a name for a grant application, and we came up with capability, hardware enhanced RISC instructions. Not good at marketing. I'm an academic. So we've been working with this with SRI International since 2010. Actually, Arm started collaborating with us in 2014, which has been immensely useful. You know, where in academia we would say, oh, look, we've done this, and there's just, 5% overhead. And Arm will come in and say, you've got 5% overhead on, things like memory bandwidth or something. No, you must do better. So, okay, so that's great. So actually, this is a absolutely brilliant example of a collaboration, I think, between industry and academia, because equally there were some things which bits of microarchitecture we were looking at and thinking, it's looking a bit big, and actually we were getting feedback from colleagues at Arm saying, actually, no, that's fine. So that, that was incredibly helpful. So today I'm going to tell you a bit about actually what is CHERI, why develop CHERI, what's the starting point, how does it work, how do we get software to run on it, and what sort of evaluations, and actually show you that if we have basically some low-level hardware primitives, we can then build much more secure software on top. And critically, it still runs the legacy stuff. So you can still run the legacy binaries without the protections, but also we've got a nice pathway. Often just recompiling the code gives you a lot of robustness, and that's great. Okay, so we bring it back to reality. So why develop CHERI? Well, here's a couple of quotes. So Ian Levy at our National Cybersecurity Centre says, buffer overflows and other sort of memory safety vulnerabilities have been with us for over 40 years. We've known about them, but they still haven't gone away. It's just embarrassing, to be frank. Matt Miller from Microsoft's Security Response Center said that they went and analysed vulnerabilities from 2006 to 2018, and about 80% of all the Microsoft vulnerabilities were memory safety related. Okay, and when you think about these, when they're looking at memory safety with bugs in this nature, this is the sort of thing where they have to patch it, they have to get something out in the field to fix it. Okay, that's the sort of criticality from their point of view. And just the cost to them and also to all of their customers in dealing with all those patches. So what we're aiming to do with CHERI is basically fix all these memory safety problems. And in first place, we've got spatial memory safety, which, so buffer overflows, buffer overreads, which CHERI very directly addresses. And then in second place, if you like, are things like use after free type bugs, which CHERI helps with a lot, although you need a certain amount of runtime support as well. Okay, so that's what we're going to do, basically trying to eliminate 70% of all the sort of vulnerabilities out there. Now, we don't promise to do everything, but I'm not going to promise that we're going to solve every single security problem, but it should make major inroads. So I'm going to walk through a couple of quick examples. I think a lot of you are quite tech savvy, which is marvellous, but just so you're aware of kind of some of the stupidity, you've probably seen this. Here's an nice XKCD cartoon. So this was the Heartbleed vulnerability that impacted the TLS protocol. So, you know, this is the protocol used to secure web transactions for banks. And due to this vulnerability in the open source implementation, you know, banks were vulnerable, any web services were vulnerable. It allowed attackers to also impersonate services, do all sorts of things. So it's a pretty nasty bug. But it's a nice classic example where all the crypto was fine. You know, all the basic security protocol stuff, absolutely perfect. What they'd missed is there was this very simple heartbeat message to keep the TCP connection live. And just every now and again, the web client will sort of say, hello, server, you still there? Say potato. 6 letters. And the server will say potato. Hello, server, you still there? Say bird. It's 4 letters. Sure enough, server says, and they're keeping the connection alive. Then the client gets a bit too clever and says, hello, server, say hat. Oh, by the way, hat's 500 letters long. And the server says hat, and then just keeps reading and reading, and you get secure, you know, you get all sorts of secret information out. I mean, this is nuts, right? But this happens time and time again. I mean, this was a major problem for web commerce. So what went wrong? How do we do better? It is actually a one-line fix, this bug. That is the fix. And it's basically just checking you don't run off the end of a data structure. And basically what we're doing in industry is saying, stupid programmer, you should have made the fix, you should have identified that. We'll patch it, ship the patch, we're done. And I would argue that you're basically just putting a sticking plaster on top of sticking plaster on top of you're not getting to the root cause of the problem. Okay. So instead, what we want to do is actually there's a lot of that information about data structures and how you want to use them actually inherent in the code. If you like, what we're doing is throwing much of that away when we compile the code. And it's partly that the instruction set, the processor, cannot understand your data structures. Okay? So we're going to do something about that. So we're going to preserve bounds information during compilation, and we're going to use the hardware to dynamically check bounds and also pointer integrity and provenance dynamically and very efficiently. Okay. Another example, so a colleague over here mentioned attack surface. The attack surface just keeps getting bigger. We write more and more applications using large libraries, and of course from an attacker's perspective, the bigger the code base, the bigger the attack surface. But what do we do to resolve that? Well, we actually know that we can apply a concept called the application, least privilege, the principle of least privilege. The idea here is that we compartmentalize an application to try and reduce this attack surface so that any particular piece of code only runs with the privilege it needs. Okay, so for software compartmentalization, we're going to decompose it to these isolated compartments and delegate limited rights to those compartments. Now, this is already done to some extent in commercial systems. So things like, the Chromium browser, each tab runs in a separate process, in a separate virtual address space, and we use that to provide isolation. The problem is it doesn't scale. Once you get over about 30 tabs, Google just pragmatically have to start sharing sandboxes because it doesn't scale. You start thrashing your virtual memory subsystem. You know, the TLB gets thrashed in your processor and so on. It doesn't scale. What we want actually is a way of doing arbitrary numbers of compartments at no additional cost. And this is actually really important. This fundamental idea allows us to mitigate not only known vulnerabilities, but it actually helps substantially with unknown vulnerabilities. You know, it's a fundamental improvement. Okay. So basically what we're trying to do with this CHERI security stuff is twofold. The first one is to uphold the principle of intentional use. So we want to basically run the software the way the programmer intended, you know, encapsulating as much information as we can about the data structures that the programmer intended to use and the way they intended to use it. And we also want to guarantee pointer integrity and provenance. And you might think in a language like C that people just arbitrarily, I thought, to be honest, that people just created pointers out of thin air at times. But actually, when we go and analyse code, much to my surprise, you really do see that, you know, regions of memory get allocated in a very sensible and hierarchical manner. And we're actually able to capture that and preserve that. And that gives us all these sort of robustness and security features. And the other one is the principle of least privilege. We want to reduce the attack surface using software compartmentalization to mitigate both known and unknown exploits. And we want very highly scalable and efficient compartmentalization. So basically, want to be able to enter and exit a compartment without much more cost than a function call. Okay, that's what we're sort of aiming for. So how the heck do we deliver this? Now, remember, kind of the best approach really in computer architecture is to try and keep things simple. You know, when we get down to the processor, we want basic building blocks on which we can build complicated software systems. Okay, so what we're going to do is replace pointers in the system with what we call capabilities, which are a bounds checked pointer with integrity and provenance properties. It's going to be held in memory and in new or extended registers. Okay, so to our address, so say we've got a 64-bit machine, 64-bit address, we're going to add another 64 bits of metadata, okay, to give us 128 bits, and we're going to add a hidden validity tag. Whenever I say this, and I've got computer architects in the audience, they usually wince at this point. You mean you're going to have 129-bit memory? Believe me, we've figured out how to sort that one out. So don't panic. The basic idea is that the compressed bounds, and I would need an entire talk in itself to describe how the compression works. There's pretty much a PhD thesis in it, and we've done formal methods and all sorts of stuff. But anyway, the compressed bounds, basically, it's a very simple idea. It points to a bounded region of memory. We've got a top and a bottom, and the address, when we dereference memory, has to sit within that virtual address space. And we've looked at, does this work with real software? So we've learned things. For example, people do pointer calculations that go outside bounds, and they will do things like, you know, add a stride pattern to a pointer and it goes out of bounds, and then they'll do a check and pull the pointer back into bounds. We've discovered, with large code bases, people rarely go beyond a 4K page. So we allow people to do calculations up to that point without anything falling over. And but every time you dereference memory, it has to be within that bounded region, and you know, you have to have the permissions. Okay, so that's the low-level building block, and we have instructions that go with this. And there again, we would need another talk. I would need to, if we had an hour's lecture, I could go through all this stuff, but we don't. So basically, we've got these instruction set additions. We've got that we can then build stuff on top of. We have low-level microarchitecture, which deals with things like, you know, these tagged memories and enforces various invariant properties like monotonicity. So what do I mean by this? Basically, you can't just arbitrarily grow your bounds, for instance. So if you're handed a capability, software can decrease the bounds, but it can't increase it. You could ask some other authority who has a higher power capability to do it for you, but you know, so you get the idea. So very low-level primitives, and then you can build all sorts of software structures on top. And we have built compiler, debugger, linker, system software, all the OS work, and applications to demonstrate that this all works. Okay. So two key applications of CHERI primitives. So we get very fine-grained memory protection. Primarily, we've been focusing around C and C++, but it should work for lots of other languages. And we actually get very strong source-level compatibility. So pragmatically, we can recompile vast swathes of code, and it just works, unless there's bugs in it. So we do find the bugs. You do have to fix the bugs. And we found bugs in all sorts of things. I mean, we found bugs in things like, you know, TC shell had a buffer underflow error that we think has been there for 20 years, you know. All sorts of stuff. We also get scalable software compartmentalization, and we've got a long way with this, but we're still advancing these techniques. But we get orders of magnitude performance improvement over the current process-based separation that's used in things like the Chrome browser. Okay. We've got a complete open source software stack. So we've got things like, Clang, LLVM, and so on. And with Arm's been working on GCC support and so on. We've been doing work with hypervisors. We've got a lot of the team I work with, FreeBSD experts, and that's liberally licensed. It's quite a useful OS to do work on because people can pick up the ideas without problems of GPL. So we have a version of the FreeBSD kernel that actually uses capabilities right the way through the OS. Arm and Linaro have been working on Android and Linux support on the Arm version of this called Morello. And then we've been porting applications to make sure all of this works. We've also thrown things over the wall to people like the Microsoft Security Response Center, and they've been analysing how CHERI would help. And so they did a study actually back in 2019, and they were looking, can CHERI mitigate vulnerabilities such that they would no longer need to issue a patch? So there may still be a bug in the code, but do they need to issue a patch? And that's what they were trying to look at. And they've written a 42-page report, and they've basically determined that in the current state that they were looking at in 2019, CHERI would have mitigated at least 2/3 of all the issues they found. And you can find the report there. More recently, a little company, Capabilities Limited, did a desktop study. So they took 6 million lines of C++ code for a desktop environment, and did various compartmentalization studies on Qt and KDE and so on. And they discovered that they had to modify 0.26% of the lines of code to make them compatible with this capabilities systems. And they got very high mitigation rate. So this is a great story. And I think one of the reasons why we're seeing such a low lines of code change is partly an awful lot of this code has gone through a 32-bit, 64-bit transition. And in a sense, we've got lucky here, because if we suddenly say, now all your pointers are going to be 128-bit, the code works because it's designed to be compatible. I suspect if we were doing this in 10 years' time, where basically everything will be running on 64-bit machines, we would probably hit problems again, just because inevitably people are lazy and they won't have checked. But right now, this is really good. Where would you like to learn? If you want to learn more, there'll be more Mark will tell you about on the Morello front. We've written various reports. There's an introduction to CHERI report that talks about the principles of capabilities and so on, and what's there in the way of languages and so on. I'm going to wrap up. So just to sort of reflect that we've done almost 12 years of work on this, and actually I meant to count up the number of PhD theses. We've done 150 research years of effort just within Cambridge and SRI in 10 years, which is kind of staggering for an academic project. And then in partnership with Arm, Arm's done a huge amount in the last couple of years to bring this Morello platform together. And really with the funding we've had from Innovate UK, we've really been trying to transition this effort. How do you take concepts out of academia and get them into industry? Well, actually, the sort of research in the lab, we had a lot of funding from DARPA primarily, but also industry, which we're incredibly grateful for. And in fact, not only did they fund the sort of research, but they then sort of funded the next part where we were really doing a lot of the engineering work to make it real. So sort of getting up your technology readiness levels up to about level 6. But then the final leap, really, which is, I'd say, where we are now, is how do you lift it from a prototype that runs applications and so on, but is still the hardware's on FPGA. It's written, the compiler was just written by a couple of people. It hasn't been really finely tuned and all the rest of it. How do you ramp up to the next level? And actually the money from Innovate UK through the Digital Security by Design initiative has allowed us to take it to that next level where we're at now. And really the challenge is getting the technology out there and getting industry to evaluate the technology so that we get customer pull and get deployment of the technology. And that's where we're at. And it's just difficult to achieve this, but I think we're showing really strong and compelling results. So I will just conclude. So CHERI protections are completely deterministic. So just remember that. There's an awful lot of security mitigation things out there at the moment that are highly probabilistic. And I would argue that a lot of the probabilistic mechanisms are very good for debugging. But usually if it's probabilistic, there's a way around them. Things like address space layout randomization, for instance, that's widely deployed. It helps, but there are ways around it. CHERI, on the other hand, is completely deterministic. It provides the hardware, if you like, with more semantic knowledge of what the programmer intended. So it pushes us towards the principle of intentionality. The code runs the way you intended it to run, not the way the attacker tricked it. We also get very efficient pointer integrity and bounds checking, and that eliminates buffer overflows and buffer overreads. If you just recompile the code, you just mitigate all of those classic vulnerabilities, and about time too, really. And we provide scalable and efficient compartmentalization. Now, compartmentalizing code does require design intent. So when you actually go to compartmentalize something, you do need to make some design choices. But nevertheless, having a very efficient mechanism allows you to deploy it at scale. And that allows us to mitigate allows us to apply rather the principle of least privilege to mitigate known and unknown attacks. And finally, we're doing the transition with ARM. And I will hand over. Thank you.
Thanks very much, Simon. Well, that's exciting. And so, collaboration with ARM. If you ask most people in my family what ARM do, they build the chips in phones, but then I correct them. ARM doesn't build hardware. ARM doesn't build chips. ARM just designs stuff. ARM doesn't build chips. But eagle-eyed people in the room will notice there's a mysterious machine that's appeared here under the screen. So that statement's wrong too. So please welcome to the stage Mark Inskip, Director of the Morello program at ARM, who is here to correct that aspersion.
Thank you. Yes, so I will go on to that and explain why we did build a chip. So my name is Mark Inskip. I've been managing the Morello program. Unlike Simon, I haven't got a slide with lots of names on, but if I did, it would have something like 200 or so names on there, because that's the number of different engineers within ARM who've contributed to Morello. So let me just first of all give you a brief introduction of ARM. I think most people know about it, but ARM is everywhere that compute happens. We've talked about PDP-11s and VAXs. When I started as a graduate, I did my first chip design on a VAX. But today, if you look, ARM is everywhere that compute happens, and that's from the world's #1 supercomputer through to really the tiniest power-constrained devices. And ARM's partners, effectively our customers, those people who license our designs, are shipping ARM chips in larger and larger numbers. 10 years ago, it was 24 billion devices. Today, over 200 billion devices have been shipped that are based on ARM. So that's just a bit of an introduction. I think most people are probably familiar with that. So let me tell you a little bit about then Morello and digital security by design. Now, as we've heard from Simon, we know security vulnerabilities are a huge problem, and that CHERI provides a lot of promise in solving them. And ARM has partners, people who want to build chips who are very interested in CHERI, but we really need to do a lot of investigation to understand just how feasible it is to to implement in a complex architecture, and what sort of issues we'll encounter and what we need to address to make it feasible to be adopted. And Morello, to be clear, is a prototype architecture. What we're doing here is we're prototyping and experimenting with something. We're extending ARM's architecture with the CHERI protection model, and with the Digital Security by Design program, we're enabling experimentation with the prototype that we've built, really to get that feedback on the questions of feasibility and those sort of issues that we'll encounter with implementation. And so, from ARM's perspective, what does success look like? Well, we're looking to find compelling uses of the Morello prototype architecture in addressing those sort of security challenges that Simon has talked about and that we know about more broadly. And if we can do that, that's going to lead to the sort of CHERI technologies being deployed in ARM processors and also potentially other architectures. I think it's worth making clear that the CHERI fundamentals aren't patented, so actually any architecture could adopt them. Clearly, from an ARM perspective, we're looking at what we can do there, but actually there's nothing preventing anybody else looking at building a processor with CHERI. But there are challenges to introducing any new architecture, and this is the sort of the commercialization chasm that Simon was referring to. So generally, what we see is over time we look at incremental improvements to architecture. So each generation has some improvements, incremental improvements that mean it's a little better, and that can be in security, in power, in performance, but it's always a little bit better than the last one, or it is until you try to bring in a substantial change. And inevitably, when you try to build in a substantial change, there's some drop-off in whether it's performance or other criteria that you're looking back to that previous generation. CHERI is one of those substantial changes, and that this problem of getting to the next level, of getting CHERI to the level where it's seen as better on those traditional parameters, no matter how good it is at security, that's one of the challenges we need to overcome. The other one is this sort of hardware-software vicious circle. So if we're looking at new software models, we need those new software models to try and justify the development of new hardware. But to develop those new software models, we need that new hardware. And it's very difficult to try to get these two things to happen together, to break out of this sort of vicious circle. And that's really what we're getting with Digital Security by Design, because UKRI, with a substantial funding of this initiative, are helping us to develop this prototype and to break that vicious circle. So these are the two things that really we need to overcome to get out, to sort of move out of the sort of, let's say, the academic approach that Simon outlined to really getting into real products. And that's what we're looking to do with the Morello technology demonstrator. So the first thing we've done to create that is to create a prototype architecture. So ARM is developing new architectures all of the time. So in a sense, this is nothing new. We start with Morello with the ARM v8.2 A-class architecture, and we extend that to support CHERI. So we've Simon's explained what the key elements are there, but we've replaced those 64-bit pointers with the 129-bit capabilities, with those upper and lower bound limits, the permissions, and of course that 129th tag bit that I'll come back to later. So that's the architecture. We then need to develop a CPU design. Again, this is something that ARM does day in, day out. What we did here is we started with the Neoverse N1, so that's an established CPU design. So it's quite a complex sort of out of order high-performance superscalar design. And we've added to that the Morello architecture. So it will still run as a standard ARM v8.2 A-class CPU, or we can run it as a Morello CPU. And that's normally where we would stop as ARM. We've developed a design, we license that, other people then go off and build chips. But what we're looking to do here is to create a prototype that we can experiment with, and the only way we're going to have anything to properly experiment with is if we create a system on chip, and that's exactly what we've done. So what we've created is quite a complex 7-nanometer chip design. So we've taken that CPU, we've integrated the CPU into the design. I'll talk more about the SoC later, but we've integrated that. We've had to modify some of the other IP in the design, so that 129th bit comes in when we have to transport that back into the DDR memory. We've added some other features as well. We used as a starting point, ARM had a development platform around the Neoverse N1 CPU. We took that as a starting point, but we've added to that, and I'll describe a little bit more about the additions we've made. And then that goes on to the Morello board. So the big shiny thing on the board there you see is the Morello SOC. On the board itself, then there's memory. So we've got a couple of DIMM slots where you can have a standard. We put a couple of 8 gigabyte DIMMs in there, so you can support up to 16 gigabyte. We've tested it with 32. In theory, we can go up to 64 gigabytes if people need that. And then we've got a number of other peripherals and interfaces around that. But it's not good enough just to have the hardware. We need also the tools to work with that. So we've created Morello versions of things like ARM's development studio. We created a tool chain, well actually a couple of tool chains, and I'll talk more about that later, debug tools and so on. And also we've got open source software available as well, and again I'll talk about that later. So those 200 engineers that I talked about in ARM, that's what they've been working on since the middle of 2019, and that led to the release of the board and the availability of a whole set of deliverables, well, a couple of months ago now. So if you want to see more about what ARM is making available, our landing page is at, as you see there, www.arm.com/Morello. If you go to that page, you'll find an awful lot of information about Morello. And if you go to the bottom, you'll see there's a resource section, and there you'll see these tiles that you can click on, and there's a whole range of things listed there that you can go to, so you can look at the architecture spec itself. There's a platform model, so we've used ARM's fast model technology to build a fixed virtual platform, so a software model of the SoC and the board, so you can use that for software development if you don't have access to a board, and that's what we've been using since 2020 to do software development. We've got the open source software, we've got tool chains, we've got a whole set of getting started documentation, and we'll very shortly have a video as well to help explain how to get started with the board. So yeah, do check that out if you want to look at the resources that we're going to have available. So talking more then about what we've developed. So Simon talked about FPGAs and so on that have been worked on. What we have here is the first silicon implementation of the sort of CHERI concepts in the Morello architecture. So what we've developed is this CPU. It's the Morello SOC actually has 4 of those CPUs. So we've got two clusters, each with 2 CPUs that run up to 2.5 gigahertz. So it's a quite powerful platform. We also have on there, we've modified the interconnect to deal with that 129th bit, as well as the memory controllers to store that in memory. We've got a couple of memory controllers so that you can connect to 2 different DDR channels for those 2 DIMMs. We also have PCI Express on the board. the SoC actually has two Gen 4 interfaces, but one of those goes through a Gen 3 switch. So on the board, you have a Gen 3 switch to a whole series of PCIe slots, and the other interface goes straight to a PCIe slot. That other interface actually also supports C6, so the cache coherent interconnect for accelerators. Just to bear in mind that PCIe, you don't get the 129th bit over that. That only goes to the memory. We've also added into the SoC a mid-range GPU and a display processor, and then you can get an HDMI output, so you can plug in a monitor so that you can, if you want to sort of run desktop applications, whether it's Linux or Android, you've got a GPU that you can do all of the graphics processing on rather than trying to do that on the CPU. And it's all on an ATX or micro ATX form factor board, which is in the shiny case there. And it's also BSA, so the base system architecture that ARM has. It's compliant, that the platform is compliant with that. And it does exist. You see it there. You see it in the photographs. So it took us a long time. So we started in August 2019. We had the kickoff meeting for this. We taped the chip out itself in May of last year, and throughout the autumn of last year, we spent our time bringing up the chip and the board to get that ready for release. We now have it, and we're now distributing it to partners. Alongside that, we have we've done a lot of work around software enablement. So that started at the inception of the program, and we've had 5 broad work streams that are listed there. And ARM's software deliverables from Morello, they're on a dedicated series of Git repositories, provisioned and managed with a collaboration with Linaro. So if you go to www.morello-project.org, you'll see there's a landing page there from which you can get to those Git repositories, and there's also quite a lot of information to support the software deliverables that we produced. And we had a couple of phases of that development. So in October 2020, we had that first platform model release, the software model, and we initially were looking to that was our own development environment, but we also made it available to others, and you can download that for free today if you want to use it. And that supported our firmware development. It also helped support the early development we've been doing with Android, and that University of Cambridge have been doing around CHERI BSD, and both of those development environments. So that was our sort of first phase. We then had a second phase driven by the availability of the hardware, and that really started in the autumn of last year, where we were looking to get the firmware ported across to work on the board, to get the board up and running, and we've looked at further developing from an ARM perspective, looking at further development of Android, and we're having ongoing development work we're doing around Linux as well, and I'll say more about that on the next slide. So that board is available now. The software is available. Just go and have a look at it. And to explain a little bit more about what we have and what you can do, the platform is really intended to enable a broad range of ecosystem activities for security researchers, software developers. The box on the right there gives you just some idea of the sort of things that we could use Morello for, but it's far from an exhaustive list. But to try to facilitate that, we're looking to provide, together with our colleagues at the University of Cambridge, a series of development environments that run on top of the standard open source firmware stack that we've provided. So I talked about, and Simon talked about, CHERI BSD, which is based on it's a free BSD derivative. A lot of work has gone on at the University of Cambridge over the years to get quite a mature solution that's available there. from an ARM's perspective, if you look at commercial devices, then really it's Android and Linux development environments that are the key environments. So we've done a lot of work around Android and are continuing to do work on Android. So we have an Android software stack that's available. We're also there's still an awful lot of work that can be done there, of course. And we're also working on making Linux available, and aligned to that is the development of a second tool chain. So both the CHERI BSD and Android are using a sort of LLVM Clang sort of based tool chain. We're now working on a GCC tool chain for those Linux developers. That's going to be available a little bit later, so we expect to have a version of that supports C around about May this year, and C++, and some extra sort of enforcement of some of the bounds and so on in the tool chain around October time. That's GCC is a bit more of a challenge because it hasn't had that same work done over the years with CHERI, so we're starting from scratch with that. But we'll have both of those available, and so people can pick and choose between the LLVM Clang and GCC from a toolchain perspective, CHERI BSD, Linux, and Android as development environments. And plus, we have proven that you can easily boot a whole number of other OSs on top of the firmware. So, having done all of this, what are we looking to get out of this? So this is a prototype. So this is something that people can experiment with. That's the key thing. Now, what we're looking for are compelling examples of how capabilities can offer security and performance improvements. So Simon hinted at some of the areas that could be a benefit, but I'm sure there are plenty of others. That's going to be backed up by red teams who will have attacked the system and demonstrated the security of the system. And then when we're talking about those compelling examples, we're looking at how that compares to what's deployed at the moment. And then we want to try and get a better understanding of how different languages and runtimes can use capabilities. So we've talked a lot about C and C++, and that's where a lot of work has been done. But, for example, we'd be keen to see what can be done with JavaScript, Java, probably plenty of others we can add to that list. Looking at how we can make use of the fine-grained compartmentalization that the architecture provides. And we're seeing that the Morello platform provides, or should be able to provide, a showcase to encourage the wider adoption of capabilities, not just, as I've said, in ARM, but potentially other architectures. It's also allowing us to experience what the right sort of SOC architecture is for building capabilities. It's not just the CPUs that are affected, particularly because of that tag bit, but we need to look at the overall architecture. And there's a lot of work going on, and we're hoping people will contribute to this, looking at how we can prove those security properties. So there's a lot of feedback we want to get over the next sort of 2 years. So the Digital Security by Design program runs to the middle of 2024. And it's worth saying, certainly from a software perspective, we're really just at the beginning. We're really just at the early days. ARM has created a whole series of deliverables to enable the platform to be used, but we're really now looking for people to experiment. And I think, for the people in the room here, this is your opportunity to get involved in this, because we're at that really exciting stage now where we're not just talking about or making presentations of this is what the hardware might be, but we actually have the hardware. It's available, it's being manufactured, it's shipping. So this is your chance to get involved, to play with the hardware, to look at ideas that you can explore in terms of making use of CHERI, of capabilities, and looking at how you can influence certainly ARM's architecture and maybe other companies as well, and try and make digital security by design not just a nice slogan, but a reality. And I think Kate is going to say a little bit more about how you actually get involved.
Okay, well, let me welcome to the stage Katie Ho, Head of Innovation at Digital Catapult.
Brilliant. Good evening, everyone. Really good to see so many of you here in person. So as Mark said, I'm going to talk to you a bit about how you can actually get your hands on this technology. So I'm from Digital Catapult. For those of you who don't know us, we're an organization really focusing on emerging digital technology adoption. And we do a lot of R&D programs, innovation, technology access, accelerators, but also really trying to enable different parts of the ecosystem to collaborate on emerging technologies. So we are delivering, as part of the Digital Security by Design Challenge, the Technology Access Program, where you will get a chance to get your hands on this technology and really experiment, test, and give us your feedback, and really work collaboratively with Digital Catapult, but also Arm, the University of Cambridge, and also the consortium partners as well, as part of the larger program. So the program is really, both in terms of an awareness program, where we'll be running a lot of these events, deep dive technical webinars in the future, to really expand the access of this technology and then innovation to a wider set of communities and organizations. But it's also a focused experimentation program where you can apply to get access to the Morello Board and work with the technologists in DC and the consortium partners to understand how it might be beneficial to your product, services, and future innovation roadmap. So you get opportunity to access the prototype architecture, hardware, some of the tools, chains, and the ecosystem that Mark and Simon talked about, but also advisors from different organizations. And your feedback and finding, as we say, will really help to inform and influence the design of future innovations in this space. So we know that companies might have different resources available. You might want to participate in the program in different ways. So we actually have 2 levels of participation for you to let us know, which one's suitable for you. So the first tier comes with 15K of grant funding, and you'll get board access for 6 months. And this is really focused on startups, small, medium enterprises, really companies under 250 employees, to experiment with the technology. You'll get an opportunity to get technical support, participate in regular check-ins with us, and also what we'll ask from you is a regular feedback and progress update, so that we know, if there's challenges that you've encountered, any problems that you've encountered, we have that conversation with you very regularly. The second tier is board access only, so that's for about 6 to 12 months, and this is an option that's suitable for larger enterprises and larger technology companies, but also potentially for smaller companies who might not be able to dedicate resource for having regular check-ins with us. So what we ask for you in this tier is really to provide us with feedback at the end of the program to let us know how you've got on and what feedback you have. So in terms of the benefits of the Technology Access Program, it's really 2 elements. The first one is early access to the technology and expertise within the consortium. Get access, of course, to things that we've talked about already, regular check-ins, practical demonstrations, technical guidance and support, and really help us understand some of the work that you're doing on the program. And the second element is the community and network. So be a part of the supported community through Digital Security by Design, be able to communicate with some of the consortium partners as well, Digital Catapult, being seen as an early adopter in this community, and really exchange ideas and feedback with each other. I think that's very, very useful, and really be visible in industry as driving innovation in this space. So, as mentioned, we're open to all types of businesses, from startups to small and medium enterprises to established companies, really interested to access this cutting-edge prototype technology. We know that there are some industries and some applications that might be particularly relevant and might be really early adopters, but for now, we're not restricting access to this program to any industries. We're really opening this invitation to technology innovators, developers, software engineers, and they're able to evaluate C and C++ products, but also beyond. So there are obviously some technical considerations of what's available in the moment. As Mark already mentioned, there's the ecosystem still evolving, so there will be up-to-date information on our FAQ on this program that will be continually updated in terms of actually what's available to you, what tool chains is available, and what guidance we're able to issue as well. So I won't go into too much detail here, but just to say that, of course, as the ecosystem develops, we'll be updating this information for you as well, so you can see what's available to you. So how do you actually get involved and apply? You're engaging with us at the perfect stage because we actually have a live open call going right now. So recruiting for our first ever cohort on the Technology Access Program. So all you have to do is register your interest on dsdb.tech, which is actually a one-stop shop for all things DSDB, where we'll be signposting to a lot of the content already mentioned by Simon and Mark, but also information on different events that are upcoming. So if you register interest on the website, you'll be sent an application form to your email, where you can let us know if you're interested in Tier 1, which is the grant funding route for smaller companies, or Tier 2. We have a set of selection criteria that you can see on the website as well, so you can know how we're assessing your application. And as long as you submit your application form by the 31st of March, you'll be considered for the first ever cohort of this program. And if you are selected, you will be onboarded by the end of May, and you'll be invited to attend an onboarding event where we'll be speaking with our technologists and also some of the consortium partners as well, and your boards will be shipped out to you prior to the onboarding event. So again, this is just echo what Mark's mentioned. This is your opportunity to get involved. We really want your feedback. We want your involvement to be part of this evolution of this innovation. So please visit dsdb.tech if you're interested, and follow us on all these channels if you want the latest updates as well. As I said, this is one of the events that we'll be doing. There will be a lot more in the coming months as well. So yeah, please keep in touch, and I look forward to speaking with you at the networking event.
All right, Q&A time. So can I ask our speakers to please come back to the stage, and can everyone please thank them again? Great set of talks there. Thank you. So we'll see how we go. We might have some questions live through the internet. Otherwise, is anyone in the room? Stick your hand up if you have questions. I've got one to prime us. If that's why you're was that adjusting your glasses? Hand up? No? Okay. Mark, I think in your presentation you mentioned C and C++ being the key languages, but there may be some advantages in other languages, and I think Simon touched on that as well. I wonder if you'd comment on what happens outside of C and C++. Are there any CHERI advantages there?
I was going to defer to Simon and better that. So it's something we've explored, but not in an awful lot of detail, but certainly it's something that we want to look at. So
I can try and tackle that. Yeah, I'm a hardware engineer, so what do I know? So if you take people are quite interested in languages like Rust, for instance. So if you write in pure Rust, the compiler will do a lot of checks or insert a lot of checks for you. So you might say, well, why do we need CHERI? I would say, well, do you want to use strings? Or because all the string libraries, as far as I can see, are all written in unsafe Rust. A lot of other stuff is in unsafe Rust, pragmatically. So I believe, and at the moment we've only done, master's level project looking at it, that by basically, if we could compile Rust and use all the CHERI features, you would basically get the protections you want in the unsafe Rust that you expect from the safe Rust, basically. Similarly, if you're linking in C libraries and things, so we did a bit of work around the Java native interface. So we got an award-winning paper out on that, where we were just looking basically, can you transition the protection model in Java all the way through into C libraries that you link against. Now the thing we haven't done yet is things like really look at Java, and there are people, academics within the broader program who are starting to look at that. And languages like Java have a very good object model, very strong object model, and actually you might, for instance, be able to treat a Java object like a compartment, for example. As I said, I'm a hardware engineer. What do I know?
I have a question here. Gentleman back.
I'm very lucky not having this. I'm very lucky not having this problem for 40 years, but I pretty much have it every morning before the breakfast. So there are two set of bugs. The one type of bug is just crash every single time you run it. Those are like very good bugs, so developers will love it. So, but the other set of bugs is like randomly deterministic. It just somehow find their way to crash on the customer site. Is that like, I'm very interested about this developer's experience. So if we somehow GCC, use your type of a GCC to compile our code and deploy on your cloud, like special cloud, and we should be able to not see those kind of randomly like bugs that like we can have a peace of mind. Those things wouldn't happen or get something.
Maybe I could take that. So if you've got buggy code, you've got buggy code, right? And it probably ought to fail. What we're trying to make sure is that if you've got buggy code, it doesn't result in a security vulnerability. But if things fall over, then you ought to get diagnostic messages back that's such that you can debug what went wrong. We also buy
some evil if-then statement causing deleting a random area of a memory. It happens all the time, right?
Yeah.
So you're going to crash the program on the customer side, or you're going to let it still run somehow magically? And let it
okay, so that's partly where compartmentalization could come in, because in that particular instance, you would like to be able to keep going, basically. So, I don't know, say if it was, to take an example, maybe it was a web browser and you've got a bug in libpng rendering an image, for instance, and you want the rest of the web page still to load, even if there's a bug decoding this image. You could potentially do that with compartments, but that requires a certain amount of investment of how you've designed the system so that you can cope with those failures. CHERI does help with the compartmentalization.
So Simon, don't forget that the random scribbles he's talking about will be out of bounds, so your bounds checker would either catch it because of bad maths in his code to start with, or the fact that it's pointing out of bounds.
Yeah, but often you do discover at runtime that it's gone wrong, so it's not going to help you as much there.
Reads random garbage that cause random crashes in deterministic code. You've still got a whole slew of things in multi-threaded code.
Yeah.
And CHERI says nothing about making that more robust.
Now, I think the one thing I will say in CHERI's defence, at the moment people are using things like address-based layout randomisation and other techniques like that. And one of the problems with those sort of techniques is you're potentially deploying an application scrambled to different customers, and it may be that only one of those scrambled variants will fall over. And that is one of the problems with a lot of these non-deterministic methods. At least with CHERI, if it's going to crash, it'll crash for everybody. But it's more likely you find the bug. Because, I mean, you do wonder, I mean, they do this with things like iOS apps, for instance. And you do wonder when people keep saying, well, this iOS app just doesn't work for me. Well, maybe it doesn't work for that particular customer, because they've got a particular instance of that code base. And that's a nightmare, right? You don't want that. You don't want randomness in something you ship.
Oh, there's a question here. Where's the microphone gone? Are we? Oh, okay. Can you just, I guess, speak loudly, enunciate?
Okay. David Bale, Tata Consultancy Services. I guess my question is to Katie. Thank you very much, by the way, that was a fantastic presentation. But have you got any view as to what sort of partners or what sort of areas of industry you're trying to develop these programs? Because I'm specifically automotive, but is there any particular area that you're going for?
Yeah, so as mentioned, at the moment we're keeping it broad, but we do know there are particular industries. For example, automotive is one of them, but also critical national infrastructure, energy, aerospace and defense, for example, that could be really interested in this. So for the first program, we're keeping it broad, but there's definitely a few industry areas that we'll look to potentially focus on later on. There's also separately a separate part of the digital security by design challenge overall, which is called Describe Hub, and they're doing some research around barriers or opportunities for industry adoption as well. So I would expect that as different parts of the program come together, we'll start moving towards potentially a bit more of a industry-focused approach. But at the moment, it's very open.
Yeah, so it feels to me like I'm a bit ahead of the game. I need to wait a few months.
Well, or you can set this, set the pace for the rest of the industry.
I would have thought it'd be really interesting,
Yeah.
particularly people who know that they've got code bases where there's been vulnerability problems, and whether you could assess would this technology have helped.
Yeah.
Because in some sense, one thing that's nice about this is it basically looks a bit like a PC. It ought to just run code. That isn't exciting in and of itself. What is exciting is if you can say, look, I've got this code base, I've ported it to this platform, and it solves all of these problems that we've had, with vulnerabilities in the system that you'd shipped. Now, that, to my mind, would be really exciting.
And I think I'd have thought automotive would be a really interesting application because
Absolutely.
actually, security there that is going to be a key thing, particularly as the semiconductor content goes up in cars and the potential vulnerabilities you're opening up with the amount of code that's now running in a even in not a car, most new cars. It really is an area that I think there's a lot of potential to have this sort of technology.
Various parts of automotive are involved in the border program as well. By the way, I'm John Godot, DSTV. So automotive is quite key.
Yeah.
Great. We had a question here. Pass the microphone over, please. Thank you.
Thank you. Hi, Jonathan Headland, Citrix. I may not formulate this question very well, but Mark, you pointed out that it doesn't have to be the ARM instruction set architecture that's used.
Yeah.
I just wondered, however, are there aspects of the ARM instruction set architecture which make it more suitable for the CHERI hardware than, for example, Intel's x86?
I'm probably biased. I'm probably biased when I say that. I guess the thing I would say is that Morello is the only prototype implementation you've got today. So I don't. Well, obviously, I don't know exactly what Intel are doing, but there isn't a prototype out there. So ARM is the platform you've got today, and in terms of the sort of the platform that we have, then actually the sort of CPU is the sort of thing that gets used it's suitable for things like anything from a phone to a car to a sort of a data center. So we have an A-class architecture. That's ARM's sort of highest sort of most complex architecture that really covers a wide range of applications. So one of the things we tried to do with the Morello board was to provide something that allowed you to experiment in lots of different areas. There's some areas that's probably not it's no good for your little tiny IoT device because it's too big a CPU, but for a lot of it covers on a broad range of areas.
If I could say, in academia we've done originally a MIPS-based version, more recently a RISC-V based version, but we haven't done CIS. We do have a sketch of an x86, which kind of looks plausible, but the devil's in the details, and so until you work your way through, and as you know, the x86 ISO is vast and complex, but we don't see why not, fundamentally.
Fundamentally, these things are all the same underneath. When you get down to the microarchitecture level, they all look very similar. So if it works as well on one microarchitecture, why not on another? The instruction level probably isn't that critical on a modern high-end core. Probably very critical further down the performance spectrum.
May I add also, from some of the comments that have been made so far, there seems to be an almost surprising amount of altruism in this industry over this particular technology. This isn't something where people are saying, well, this is mine and I'm going to patent it and have everyone license it. It's this works if all of the boats rise. This works if all software is improved, and there's, I would say an outright motivation to see it on other architectures as well as just ARM and MIPS, RISC-V.
actually, Matt, I'd just expand on that a bit. We're very keen for other architectures to adopt this because it isn't really much use if only ARM adopts it. You know, we want the whole world to adopt it and be
all architectures to adopt CHERI. Yeah. Good point. Thank you. There's another question.
Hi, I'm Stein from Shen Technology. I got the point about stopping buffer overflows and stuff like that. Does CHERI address anything with data being encrypted, either program data or data storage being encrypted? Yeah.
Could you speak up a little? I'm so sorry. Could you repeat the question a bit louder? The microphone seems to.
No, I think that's for the live streaming only.
Oh, okay.
It's not reinforcing. It doesn't really. If I can sort of paraphrase, so it doesn't really help on sort of dealing with, say, data that's encrypted at rest, for example.
Yeah.
No, it's an orthogonal technology, really. Yeah. So that's one of the things that I think sometimes people... It's funny, sometimes people say, well, does CHERI use encryption? It's like, no, there's no encryption anywhere. There is this hidden validity tag, which is absolutely critical to the security properties, but it doesn't rely on encryption at all. So you could still apply encryption technologies, but as I said, it's very much sort of orthogonal space.
And multiple solutions to multiple problems, and they all seem to dovetail quite nicely, which is...
Yeah.
And another here.
Thank you. Adam Greenwood-Byrne, Roll VNC. Can I just ask a quick question, probably to you, Simon, around CHERI? Thinking where this might end up, like, for example, in single-board computers, what CHERI advantages might there be for things like memory-mapped I/O and protection for peripheral access in that way? Or is that a really naive question?
No, that's a really interesting question. So we've looked a little bit at CHERI for microcontrollers. It's sort of interesting. Often microcontrollers have a memory protection unit, and you often get 8, 16 regions, and it's a fixed number. And the funny thing is, if you look at that microarchitecturally, it's often an associative memory, basically. So it actually consumes quite a bit of power. And you don't need it once you've got capabilities. So actually, one of the things we're interested in is, can you have an arbitrary number of protection domains and at lower power, which looks plausible? Can you then apply it to I/O? Well, obviously, if it's memory-mapped I/O, you can restrict what regions a piece of code has access to. Absolutely. There's then another question, if you've got accelerators or other devices that can be bus masters, could they use capabilities? And we've started to look at that. But that's still an area, and also what do you trust? Is that little bit of I/O just a bit of IP that you've purchased, and you kind of trust them, but you probably say trust them, but it might be buggy, and maybe you wouldn't want it to trust it. So one of the things we were looking at is, could you have something like a capability list unit? We refer to it as giving a legacy thing clue. A capability list unit, sorry, bad joke. So we've been looking at these ideas, and I'm not sure how much I can say. I know Arm research have been having a bit of a squint at it. Probably shouldn't say any more than that, but it looks quite plausible.
Okay, thank you, that's really interesting. Thanks.
So first of all, I just wanted to say I should still like to hear about this validity bit, because I'm not sure we covered that in detail. 129 bits, I'm guessing you're hiding it somewhere in the 128 today.
Yeah.
But the question I was going to ask was an extension to the previous one, which was, you focused on buffer overflow because that's the most common one you see. The idea of a capability sounds intriguing. Is there potential to extend that to other types of vulnerability? And I'm thinking maybe of the timing analysis, which is another question I was thinking of. Maybe you're making it easier for timing analysis with this discuss. Higher up the level, some of the other things like SQL injection, that's kind of silly on the part of a programmer, but somewhere in the middle there are other things which you could address with the same idea.
Do you want to do that bit, and I'll talk a bit about how we handle a 129th bit?
Okay, we can do a bit of it. So, I think timing analysis, we don't really have anything to say about it. There again, it's a sort of an orthogonal problem.
Have you opened it wider with the technique?
I don't think we have. We have been looking at things like speculative execution attacks, transient execution attacks. And actually, we looked at ARM just at the point where all that got opened up. And CHERI helps in some areas, but not others. And we've actually been looking a bit further. Can we use these mechanisms? Because you've got an idea of, what regions of memory you should be allowed to have access to within a particular protection domain in which the code is running in. So it can certainly help. Now what else can I say? I think that's, I'll probably leave it there. Okay. But it's definitely more than just buffer overflows. It's the actual provenance of where pointers have come from. And to give you another example, we not only are pointers used for data pointers, but they're also used for code pointers. So, for instance, we put return addresses on the stack, turn into capabilities. And then if you've got things like return-oriented programming or jump-oriented programming attacks, it mitigates those, because if you overwrite those with data, it's no longer a valid capability.
So self-modifying code.
So, people do it to attack systems, and there's a lot more to it than buffer overflows.
Okay. So when it comes to that 129th bit, so that's where we couldn't just modify the CPU, but we had to be able to transport it around the system, which wasn't too difficult. But also on the memory controller side, you can't go out and buy 129 byte bit memory. So it works with standard memory, and we've got a couple of strategies in the way that additional bit is written to the memory. So I won't go into all the details now, but there's a couple of approaches so that you're just using standard memory. And then one of the key things we want to look at is to see what sort of impact that has in terms of the overall performance of the system. But the key thing is we've got that extra bit, but we need to be able to still just use standard off-the-shelf memory, which is what we've got to plug into the board.
I guess how and when is that set?
So how
and when is that set and used?
So that's okay. So it's okay. It's a bit of detail.
There's quite a bit of detail. I mean. Yeah. One approach, for example, is we just store the tag bits in an upper bit of memory, so you just allocate a bit of memory, and then we cache it. But it turns out there are lots of cunning tricks you can use, and in particular, before an application is allocated memory, the region's zeroed, so it has no tags in it. And it turns out there's all sorts of things we can do when you just allocate memory to an application. It's like, have another page that's got no tags in it. And you never need to read this tag information. It ends up all being stored in cache most of the time. There's lots of tricks we can play. And actually, we just got the benchmarks now for a large amount of code. We see fractions of a percent in terms of DRAM overhead. That was one of the examples where I said early on that we were seeing sort of 5% overhead, and ARM said, no, because that's 5% of quite a lot of your power budget. For a lot of devices, so that's not acceptable. So we did a lot of work in collaboration to get it down to, as I said, things like my bench. It's pretty much negligible.
Yeah, and so that's using the standard memory that you might get in a phone.
Yeah.
The other approach we've used is we use ECC memory, and then rather than having a 64-bit beat, we have a 128-bit beat, and then we use those freed up ECC bits to store the.
So this would be an excellent topic, or an excellent time to depart to the atrium and have a beer and discuss tag bits in more detail. Yeah. So there are free drinks outside. Please stick around and carry on these excellent conversations over the refreshments. Thank you very much for coming. Let's thank our speakers. Let's see you outside.